So 10.5 is, in a sense, basically review of what we've already gone over in the Unit 2 POGLs that we did, but the standards are for AP Chem are kind of split between units on these, and 10.5 in the book goes over all of them again. So a lot of this should be things that you've already seen. So I put the standards here at the front that you could read them all together as kind of a reminder of everything after you see this recording if you want to, or if you just want to read it and later or whatever. But we'll go through them as we're talking about it. So first of all, we have crystalline solids. We're talking about different types of solids, different types of solid matter. So crystalline solids are solids in which the atoms, ions, or molecules are arranged in a definite repeating pattern. This is different than amorphous solids, which are not crystalline. So this is formed when a liquid freezes before its molecules become arranged in an orderly pattern. And so you can see a comparison here. In amorphous solids, the molecules didn't freeze with a lot of time. They were frozen very quickly, and so they didn't get in a nice normal crystalline pattern. So this can be used to make things like glass, to shape it into whatever structure is needed by cooling it really quickly, I believe. I don't know a whole lot about glass making, but if the molecules don't have a whole lot of time to cool in their rigid pattern, then they can end up kind of out of pattern, basically. But here's another image of that, and you can see the difference. On the right, it hasn't cooled, and so it's amorphous, and on the left, it hasn't had time to cool, and on the left, it has had more time to cool, and so it gets its normal arrangement. But I'm going to say, even though 10.5 in the book covers that, excuse me, I have a bad cold. Even though 10.5 in the book covers that, here we're not going to cover that too much because I don't think it's a huge part of the AP Chem standards. But the different types of crystalline solids really are. So we have ionic solids. Ionic solids are composed of positive and negative ions. And so as the standards say, you need to be able to represent an ionic solid looking at models, which we've already done quite a bit of. And you need to understand that the cations and anions in an ionic crystal are arranged in a systematic, periodic 3D array that maximizes attractive forces and minimizes repulsive forces as per Coulombic attraction. So understanding, right, that the positives are away from positives, minimizing repulsion, and vice versa, and that the positives are close to the negatives, increasing attraction, which we know the more attraction, the lower energy. And so as a result of that, you should understand properties of ionic solids, including high melting points, because due to those very strong attractions between the ions, it takes a lot of energy to separate the atoms from each other. And so if it takes more energy to separate them from each other and cause them to move around each other, if that takes a lot of energy, then they have high melting points as a result. And they're hard and brittle and shatter instead of bending. This should make sense because the positives and negatives are interlocked. And so you can't just slide, it's not easy to slide individual atoms past other individual atoms because then you're putting positives next to positive, negatives next to negatives. So instead, what's more energetically favorable is for it to shatter instead of bend. So if you have like a larger rock crystal or something, and you try to bend it, it will shatter before it bends, usually. And so this is what the standard says here. Due to strong interactions between ions, ionic solids tend to have low vapor pressures, high melting points, and high boiling points. So it tends to take a lot of energy to melt them or to evaporate them. And they tend to be brittle due to the repulsion of like charges caused when one layer slides across another layer, as I was just saying. It's hard to move positives next to positives. They conduct electricity only when the ions are mobile, as when the ionic solid is melted or dissolved in water. So that's something you should know, that ionic substances are going to conduct electricity not in the solid phase, but they will in the aqueous phase or as a liquid. Then we have metallic solids, and metallic solids are materials that consist of metal ions exclusively. And so they're often described as a uniform distribution of atomic nuclei within a sea of delocalized electrons. So you remember describing the different types of bonds, where we have covalent bonds, where the electrons that are being quote-unquote shared are more likely between the two nuclei, which increases the attraction and minimizes the repulsion. We have ionic bonding here in C, where there's more attraction for one nuclei than the other due to electronegativity differences, and that's the lowest energy configuration, so the electrons are on average closer to one atom than the other. And then here we have in B, where both electronegativity values are low, and so the electrons are more delocalized and they're more spread out in the structure. That's a metallic solid. So this could, for example, be lithium with potassium. Neither atom strongly attracts the electron, and so this is metallic. And again, it could just be one element like here. So it could be pure copper, or it could be a mixture of different metallic elements together. And so metallic solids have high thermal and electrical conductivity. And again, it's a sea of shared electrons to share energy between atoms. So the thermal energy or the electricity can easily be spread about in a metallic solid. And so this is why, for example, they're good if you have like an electric oven, because the metal is conducting heat. So you can conduct electricity into the metal, and then the metal can conduct heat out very easily. And they also have luster. Because the electrons are delocalized, they reflect light. That's what luster means. It's reflecting light. So shiny, ooh, right? That's metals. Shiny, ooh, okay. And they're malleable. The atoms can move past each other relatively easily. So unlike an ionic solid, where it's not easy to slide one past one another because then the structure is quote unquote messed up, because then you'll have positives next to positives or negatives next to negatives. Here, if you're moving one copper past another copper, well, it's just a copper replaced with a copper. So it's not hugely energetically unfavorable to do that. So the metals are actually more malleable. Now, you might think, but the metals I encounter in my daily life, like this laptop, right, are not malleable. Like this is hard metal. Well, that gets into when we talk about interstitial alloys and things like that, where alloys can be made to increase the rigidity of the metal. But if you think about like one element in a metal, so if you, for example, remember when we've had copper that we've taken out of the lab and used in experiments, or like aluminum foil, or like pure copper wire, those are very malleable and bendable, right? So the pure metals as metallic solids have this property. Again, alloys can be used to change that, because obviously there are many cases where you want your metals to be not so malleable. And as a result, they are also hard and strong. So let's read the standard here. Metallic solids are good conductors of electricity and heat due to the presence of free valence electrons. They also tend to be malleable and ductile. Ductile, like you can spread it out in a line, due to the ease with which the metal cores can rearrange their structure. However, in an interstitial alloy, interstitial atoms tend to make the lattice more rigid, right? So especially if we have like a carbon alloy or something, decreasing malleability and ductility. Alloys retain a sea of mobile electrons and so remain conducting. So if you think about hard metals that you see in your daily life, well, those are alloys. And like the really hard ones perhaps have carbon in them or something like that to give them a lot of rigidity, which we talk about later in this recording. So again, metal solids, malleable, don't shatter, hard and strong. We have covalent network solids. These are minerals with networks of covalent bonds. And due to the high energy to break covalent bonds, they tend to be hard with high melting points. Common student misconception, excuse my cough, I am not used to this weather. It is very cold today. When I woke up, it was -19 Celsius, and I am used to Senegal weather, and I just got here, and I'm not used to waking up to -20 Celsius. Common student misconception is that the if it's covalent, then it's automatically not a high melting point. But students forget about covalent network solids because for covalent network solids, that is not true. Because to melt a covalent network solid, it actually requires breaking the covalent bonds. And so sometimes the covalent network solids can actually have higher melting points than most other solids. And sometimes they can be even more hard. They can be even harder than like most other solids. So like for diamond, for example, right? Gentlemen, you go and propose to a lady. You propose to a lady not with an ice ring, but with a diamond ring and gold. And why do you use diamond? Because diamond is very hard. It is not brittle, and it's very rigid. It's a covalent network solid, so it doesn't break down. And so that's one of the types we can think of here. So, in covalent network solids, the atoms are covalently bonded together into a three-dimensional network, or layers of two-dimensional networks. So, three-dimensional network would be diamond. Two-dimensional networks would be like graphite. So, graphite is like in pencils. Now, when you draw with graphite, you're not actually breaking covalent bonds because as you can see in the image here, it sheets. So, an individual sheet of the carbon is coming off, but these are not strongly connected together. So you're rubbing the sheets away from each other, but you're not breaking the carbon bonds between them. That would be like trying to write with a diamond pencil. That's not going to work, right? These are only formed from nonmetals and metalloids. So elemental, like a diamond and graphite, which are carbon, or binary compounds like silicon dioxide or silicon carbide. Due to the strong covalent interactions, covalent solids have high melting points. Three-dimensional network solids are also rigid and hard because the covalent bond angles are fixed. However, graphite is soft because adjacent layers can slide past each other relatively easily. But you're not breaking the covalent bonds in graphite. But if it's a three-dimensional network solid, it's very, very hard, and you're not breaking apart any part of it. So covalent network solids are different than molecular solids. Molecular solids are compounds that are solids just by intermolecular forces. So these are composed on neutral molecules, not covalently bonded together like in covalent network solids. So for example, carbon dioxide, we just have London dispersion forces. Iodine, just London dispersion forces, holding the molecules together in the solid state. So that's much easier to melt because what's being broken are London dispersion forces and not covalent bonds. And so these tend to be smaller and symmetrical in the individual molecules. Therefore, a nonpolar molecule, or sorry, I'm running ahead of myself. In terms of molecular solid properties, smaller, symmetrical, and therefore nonpolar molecules have weak attractive forces and very low melting points. So, for example, hydrogen, nitrogen, fluorine have very, very low melting points because they're all molecular solids and their London dispersion forces are very, very weak. And so you don't really readily find them. Like, it has to be very, very cold or very, very high pressure for them to be found in the solid state because obviously hydrogen, nitrogen are in the air around us. Carbon dioxide in the air around us, oxygen in the air around us. The pressure has to be very high and or it has to be very, very cold to actually find them in the solid state. Molecular solid properties. Larger nonpolar molecules have larger attractive forces like water and higher melting points because of stronger dispersion forces. So water has hydrogen bonding, which means that it's a higher melting point than like hydrogen, nitrogen, and fluorine. And then even more than that, if you have something like butter or another fat that is a solid at room temperature, well, those are long carbon chains. So even though they all, quote unquote only have LDF forces, those LDF forces are really strong, and so they can potentially have a higher melting point than even water. Excuse me, due to the strong London dispersion forces. And so those must be overcome to melt them. But of course, the melting point is still much weaker, or still much lower, I should say, than like a covalent network solid or a metallic solid or an ionic solid, generally. And then polar molecules also have higher melting points. So if it's a relatively higher melting point for a molecular solid, then it will either be a large nonpolar molecule like a fat, or it's a polar molecule that can dipole-dipole bond or hydrogen bond like water, something like that. And so let's read this standard. Molecular solids are composed of distinct individual units of covalently bonded molecules attracted to each other through relatively weak intermolecular forces. Molecular solids generally have a low melting point because of the relatively weak intermolecular forces present between the molecules, as I've been saying. They do not conduct electricity because their valence electrons are tightly held within the covalent bonds and the lone pairs of each constituent molecule. Molecular solids are sometimes composed of very large molecules or polymers. So again, they're not conducting, but there are cases of molecular solids that have very large molecules, and those might have like higher LDF forces just due to their size. And following up on that, in large biomolecules or polymers, non-covalent interactions may occur between different molecules or between different regions of the same large biomolecule. The functionality and properties of such molecules depend strongly on the shape of the molecule, which is largely dictated by non-covalent interactions. I need to look at the FRQs for Unit 6. Although this is a standard, I can't even think of any MCQ Unit 6 problems that have really asked anything that is assessing this. But it's something that comes up a lot in AP Bio, that, like, when we talk about proteins in AP Bio, there are these long molecules, and yes, they have covalent bonds, but they're so long that different parts of the molecules interact with each other through all sorts of interactions that are not covalent bonds. And so that's just something to be aware of. I haven't even seen it. I have to check the FRQs. Maybe it'll come up in those when I look, but it doesn't really come up, but it's something to be aware of and something you definitely know if you took AP Bio. So here's a nice overview table of everything we talked about, and these should look familiar because these images, and you could pause this and take a long time to look at this, or you could just go back to Unit 2 and look at your types of solids POGO from Unit 2, because that's where these images come from. So as you can see, this is a review of everything we've already covered, and so you can go ahead and look at this and these images. And this is one from your book, the openstax book, and I like this one because of the visuals, and also you need to know how to visually represent things, as the standards have been saying. And AP Chem likes to assess you by showing you visuals. Graphing is pretty cool. So the idea of graphing is, yes, graphite, you have a single layer that slides past another layer. So it seems like, you can easily break apart graphite, right, in a pencil or something. Yeah, it breaks off as you write. But graphene is taking an individual layer of the graphite and saying, okay, if I take one layer thick of these atoms, it's super thin, but super strong because it's covalent bonds that aren't easily broken. So you can have a very thin, super strong material. And so there's lots of innovation going on and thinking about uses of that. So if you're curious, you could look up and Google like graphene uses or graphene material of the future and see what comes up there. I think it's quite interesting. And I haven't looked at it in a couple of years, so maybe there's even more new ideas. Sorry, this cold is killing me. Okay, the last thing, again, we've also already talked about this, but it comes up in the book again, is we have interstitial alloys and substitutional alloys. Interstitial alloys form between atoms of different radii, where the smaller atoms fill the interstitial spaces between the larger atoms. So if you have one smaller atom, like for example carbon, is a lot smaller in radii than a lot of metals, it'll fill up spaces in between, as you can see here. Where substitutional alloys, there's a substitution, where you have metals of similar size, and one or the other is there instead of the other. So, yeah. So, metal alloys, the definition of a metal alloy. Oh my goodness. Ah, this is cold. Is a metallic substance composed of two or more elements, both metals. And then we have those two types, substitutional and interstitial. So again, as I was saying, substitutional alloys are when the atoms are relatively similar in size. The atom exchange method usually happens, where some of the atoms composing the metallic crystals are substituted with atoms of the other. Just like if you are listening to this as I'm recording this, you have a substitute teacher, because I'm not there because of craziness, right? Unfortunately. And so somebody is in my place substituting. But interstitial would be like if another teacher was inside of me. Okay, I don't know. But, right, substitute. You're familiar with that term. So you can see here's just another image showing the same idea. Then interstitial. One atom is usually much smaller than the other, so it cannot successfully replace an atom in the crystals of the base metal. The smaller atoms instead become trapped in the spaces between the atoms, called the interstices. And this makes it a very rigid structure because it prevents the atoms from sliding past each other. It's kind of like, my analogy for this is if you're in a crowd of adults and then there's like little kids, it makes it really hard to move around because you can't slide past the other adults because there's a little kid there in the way. Okay? So this atom, even given lots of force and pressure, would not slide past this other atom very easily because there's an atom in between in the interstitial alloy. Now, as I said before, in an interstitial alloy, interstitial atoms, as according to standards, tend to make the lattice energy more rigid, decreasing malleability and ductility. Okay, so that is it. Again, as you could see, it was a lot of review of past information, but it is nonetheless 10.5. And I'd suggest if you don't remember anything, just gaze at this beautiful table from your previous Pogles for a couple minutes, and I think it will come back to you. And maybe sip some tea or something, just stare at it in its wonder, and remember your types of salts. There you go.